SwayamPrabha. Digital India. Educated India.
So, we consider Zhukovsky's transformation. Which we consider now that the transformation will map an airfoil in the z plane to a circle in the zeta plane. That is the geometry, whatever is on the z plane, that we are calling an airfoil, and this is mapped onto a circle on the zeta plane. For the circle, we have two free parameters, the radius of the circle and its center. And for this transformation, we have two critical points which are at zeta equal to plus minus b. So, this transformation has two critical points. Now, of course, if we place the critical points on the surface of the circle, then at those 2 points the angle will not be preserved, and we have seen that the angle on the circle plane, which is 2 pi, will become 0 on the airfoil plane, which we have seen yesterday itself, that the angle on the circle plane at all the point is 2 pi on the surface of the circle, pi, where the two curves are intersecting. This angle will transform to 2 pi, and consequently the what we call the trailing edge angle, or the angle at that contained by the curve, that becomes 0. So, since there are two critical points, if we have both the critical points on the surface of the circle, then the transformed geometry will also have two such sharp corner, because at the critical points the transformation is not preserving the shape, not preserving the angle, and the smooth surface, that they become sharp corner. So, if we have both the critical points on the surface of the circle, then we will get two such critical point or two such corner on the transformed geometry. So, at least for an airfoil which has a trailing edge, we must have one of the critical points on the surface of the circle, the other critical point of course must not be in the on the surface of the circle, if we do not get, if we do not want two sharp corner. We say that the velocity, the complex velocity will transform according to this rule, that complex velocity on the z plane will become the complex velocity on the zeta plane divided by dz d zeta. Now, see at the critical point what will happen? At the critical point dz d zeta is 0. Then unless w zeta itself is 0, then w z will become undefined. Now, since the flow over an airfoil is a real practical problem, obviously there will be not a point on the airfoil surface or anywhere in the flow field where the velocity is infinite, it is not possible. In any physical problem this infinity is not possible. So, since that point corresponding to the critical point on the circle is not a singular point on the airfoil plane, this W zeta must be 0 at zeta equal to plus minus b, should be. That means, this will now give us or will help us to find the value of circulation. If you remember that the circulation, the value of circulation we could not find for a cylinder, for a circle. We said, okay, if the value of circulation is this, then the stagnation point will be here. If the value of circulation is this, then the stagnation point will be here, and so on. We consider various possibilities. But if just a given circular cylinder, we cannot say what should be the value of circulation. But now you see that when we think the flow about an airfoil, we can enforce that what should be the value of the circulation, because of this requirement, that wherever we are making the critical point, provided the critical point is on the surface of the circle, that should be a critical stagnation point, that should be made a stagnation point. Reason that if since that point is being transformed to the trailing edge of the airfoil, and at the trailing edge of the airfoil the velocity is not infinite. Eventually, this is known as a very famous condition called Kutta condition, which simply Kutta condition KUTTA, a Kutta condition, which says that for an airfoil the flow should be such that it will always leave the trailing edge smoothly. It will always leave the trailing edge smoothly. See what is the implication of that. See, considering the physical problem, let us see what we get. Think about an airfoil. Our boundary condition states that the flow must be tangential to the surface. For an inviscid flow, the flow must be tangential to the surface. Of course, in a viscous flow, it is no slip, that is everywhere the total flow velocity is 0, both the tangential and normal component are 0, but in inviscid flow the flow is tangential to the surface, both on the upper surface and lower surface, meaning that the streamline adjacent to the airfoil surface is parallel to the airfoil surface. The streamline which is parallel to the adjacent to the airfoil is parallel to the airfoil surface. So, that is if we consider a streamline on the upper surface, that streamline is just say parallel to this, and on the lower surface also this streamline is parallel to this. So, these two streamlines, what will happen? Following their original path, if we follow the original curve, then they will intersect at the trailing edge, but we know that two streamlines cannot intersect. The two streamlines cannot intersect. This gives that one streamline is coming like this, another streamline is coming like this, and at the airfoil, if the airfoil has a finite trailing edge angle tau, if it is a finite trailing edge angle tau, then these two streamlines is intersecting here. But we know two streamlines cannot intersect. So, this is the situation that will not occur, this situation cannot occur. What will occur is something like this. That these two streamlines will merge and become one streamline, smooth. And how is that possible? That is, at the trailing edge the velocity must be 0. At the trailing edge the velocity must be 0, or the trailing edge must be a stagnation point. That is, when the trailing edge angle is finite, the trailing edge must be a stagnation point. That is what is the meaning of that the flow must leave the trailing edge smoothly. However, we have seen already that the Zhukovsky airfoils have a cusped trailing edge, that is, the trailing edge angle is 0. What will happen in that case? The Zhukovsky airfoils are cusped. And what is the meaning of this? Then let us see that. Consider a Zhukovsky airfoil. The trailing edge angle is 0. Now, the streamline on the upper surface and lower surface, you see they are not intersecting. The streamlines on the upper surface and the lower surface, they are parallel to the airfoil surface. Upper surface streamline is parallel to the upper surface, lower surface streamline is parallel to the lower surface, and the upper surface and lower surface of the airfoil, they are parallel to each other, meaning that these two streamlines are also parallel to each other. Then it is not essential to have that velocity 0, but both the streamlines must represent same velocity, because this trailing edge point, which is one point, at one point of course you cannot have two velocities. So, there will be only single velocity, but it need not be 0, it can be anything, any finite value. So, in this case this is flow velocity, of course, flow velocity at the trailing edge is finite. Sometime it may be 0, but it need not be 0 in general, it can be anything, a finite value. So, this is the implication of that Kutta condition, that the flow must leave the trailing edge smoothly. Essentially that translates to that if the airfoil has a sharp trailing edge, then the trailing edge must be a stagnation point, but if the trailing edge is cusp trailing edge angle is non-zero, in that case the trailing edge need not be stagnation point, but the velocity at the trailing edge must be a finite value. So, now going back, the W corresponding to the Z trailing edge is finite. either 0 or non-zero, finite 0 or non-zero. So, if zeta equal to b corresponds to we have assumed that zeta equal to b, that critical point is transformed to the trailing edge of the airfoil. Let us assume that whatever is the zeta equal to b, that critical point transformed to the trailing edge of the airfoil. At the trailing edge of the airfoil, there is this w z, this is finite, okay, and at the critical point this is 0. So, if this has to be finite, then this must be 0. And this will now help us to find the value of circulation. You see, lift, as you have seen already, is directly proportional to gamma. The magnitude of lift force is simply rho q infinity gamma, that we have already evaluated, and the value of gamma is now fixed by this condition, that wherever we are placing our critical point, that must be the stagnation point. That must be the stagnation point, and then that will fix our value of circulation or the value of lift, or the circulation or lift should be such that flow must leave the trailing edge smoothly. When a wing or airfoil starts its motion, it develops a circulation, and the circulation should be such that the flow leaves the trailing edge smoothly. Okay, that is what is the significance of Kutta condition, and you see the essential, how essential Kutta condition is. Without that Kutta condition, we are not in a position to find the value of lift or find the value of circulation. So, in inviscid irrotational flow, we cannot, if you remember, we earlier discussed that to find a unique solution, we need to specify other than the boundary condition. The boundary condition of course has to be specified. Other than that, we need to specify a cyclic constant. Without that cyclic constant, we cannot get a unique solution. And that cyclic constant we can fix if we are considering flow about an airfoil, where we have a sharp corner. For a circle, we cannot fix the value of circulation. There is no Kutta condition for a circle, and hence the value of circulation cannot be fixed for flow about a circular cylinder or flow about a circle, and we do not have unique solution for flow about a cylinder. But for airfoil we have that unique condition, because there is a Kutta condition which helps us to fix the value of circulation uniquely. Okay, now let us consider then this transformation, and let us see what happens to first of all the value of circulation. So, that we can complete our complex velocity first. Let us consider we have this Zhukovsky airfoil which is transformed to a circle. So, this is the center of the circle and this is its radius. Now, I said that we have two free parameter, the center of the circle and its radius. Okay. That means, where should be, what is the position of this center? We are saying this is the center, where the point doublet and the point vortex is placed. Flow about a circular cylinder is uniform stream plus a point doublet at the center plus a point vortex at the center. So, this is the center at which point vortex and point doublet is there, but where is the center? That means, where is my coordinate system, where do I place my origin? Let us say we place the origin in such that this is this. Zeta plane, and we call this axis say xi and eta. We call this position of the center is zeta naught. And we write that the magnitude, let us say what notation to use. Okay. Sorry, no. Let us come to this little later. First of all, point. See, this is then, and let us consider this is that B. this is what is B. Then this point will become the critical point, okay. And this is what will become this trailing edge point, and this angle let us say take beta. The center of the circle is at zeta naught, then any point on the circle, how they are obtained? What is the equation of the circle? See, if the center coincides with origin, then the equation of circle is r e to the power I theta. If the center coincides with the origin of the coordinate system, then it would have been zeta equal to r e to the power I theta. But now the center is at zeta naught, then what is the equation of the circle? Is zeta minus zeta naught equal to r e to the power I theta. So, that is what is the point on the circle. What is the trailing edge point? Now, if we look back to that expression for the complex velocity on the circle plane, complex velocity on the circle plane, or zeta plane. Remember that expression W zeta equal to q infinity e to the power minus I alpha, the general case, plus what we had, I gamma by 2 pi 1 by zeta minus zeta naught plus or minus what are the expression, minus q infinity r square e to the power I alpha no, divided by zeta minus zeta naught square. So, let us find out the velocity at the trailing edge. The first term, of course, second term I gamma by 2 pi. So, this is not 2 I gamma by 2 pi the second one. Okay, write everything q infinity r square e to the power I alpha r square e to the power minus 2 I beta. Now, according to Kutta condition, this is 0. So, what do we get? Q infinity e to the power minus I alpha plus so how much is gamma? Is multiply throughout by minus I e to the power minus I beta 2 pi r, multiply throughout by minus I 2 pi r e to the power minus I beta. What happens if you multiply by that minus I e to the power minus I beta 2 pi r? This q infinity I have missed. Okay. So, what is gamma? Now, gamma equal to 2 pi r q infinity so much. Look to that first and last term, both of them are nearly same. One is multiplied by e to the power minus I alpha plus beta, the other one is e to the power plus I alpha plus beta. So, out one, either the cos or the sin will get cancelled. Which one? Okay, one of them is multiplied by minus I, the other one is multiplied by plus I. First of all, you must remember that this gamma, without doing anything, that this must have a real value. It will not have a complex value, it will have a real value. And since these are multiplied by I, that the sign will be associated with the real, sign will give the real part. So, this is 4 pi r q infinity, 4 pi r q infinity sin alpha plus beta. So, this will be the circulation produced for the Zhukovsky airfoil or for the airfoil, 4 pi r q infinity sin alpha plus beta. You see that the circulation of course depends on alpha, which is the angle of attack or the flow inclination with respect to the chord, and also a beta, a relative location between the center and the critical point, or which has later become the trailing edge point of the airfoil. We will see later on what is the meaning of this, what it says. You see, at this stage it tells the circulation only depends on the free stream velocity, all right, angle of attack and this relative location between the center and critical point or trailing edge, or the rear stagnation point, the center and the rear stagnation point. Now, of course, we can find what will be the lift force. Lift force is and the lift coefficient for the airfoil of course is the lift by half rho q infinity square into c. The planform area of the airfoil is c into 1 unit span. This lift is also per unit span, and this gives what? Rho q infinity square gets cancelled, it becomes 8 pi r by c So, this is what is the lift force or lift coefficient. Now, let us find the velocity at any other point. What should be the velocity? Now that we have circulation known, what will be the velocity at any point on the first the surface of the circle, then what will be the velocity on the surface of the airfoil. So, the complex velocity on the surface of the circle what we have? W zeta equal to q infinity e to the power minus I alpha I gamma by 2 pi. I gamma by 2 pi, gamma is 4 pi r q infinity sin alpha plus beta. So, by 2 pi, so this becomes simply 2 r q infinity sin alpha plus beta. And what is that zeta minus zeta naught? R e to the power I theta. Now, it is I theta, not beta. That r also gets cancelled. So, what remains? What remains? 2 I q infinity sin alpha plus beta into e to the power minus I theta. Okay. And what happens to the last term? Last term is minus q infinity e to the power I alpha e to the power 2 I beta. Simplify. Oh, not 2 I beta, this will be 2 I theta, no? Beta is only for the trailing edge. You can simplify it. Minus? What the last term? Yes, what happens if you simplify it? Let us take out this q infinity e to the power minus I theta. Then the first term becomes what? E to the power minus I alpha minus theta. Okay. The second term remains 2 I sin alpha plus beta, and the last term remains the first and last term, first and third term. What do they become? Minus sin alpha minus theta. Of course, or 2I. So, that 2I also comes out. These two also gives 2I sin alpha minus theta. So, that 2I comes out. So, it becomes 2I q infinity sin alpha plus beta minus sin alpha minus theta into e to the power minus I theta. So, this is now the velocity on the surface of the circular cylinder, which corresponds to the airfoil. Remember, you cannot use it if you are dealing only with a circular cylinder. These you can use only when you are dealing with an airfoil, that airfoil has been mapped to circular cylinder. Okay. Just a simple circular cylinder and you are talking about flow about a circular cylinder, then you cannot use this, because in that case the value of circulation is not fixed. The circulation is fixed because of that airfoil. The circulation, the value of gamma is fixed because of that airfoil, not because of the circular cylinder. With the circular cylinder you cannot fix gamma. So, none of these formula can be used for just a circular cylinder. Now, let us find the velocity at the trailing edge. Quickly, how much will be the trailing edge in the jet plane? Location of the trailing edge. You see the trailing edge zeta equal to b. Okay. So, the transformation gives z equal to 2b. This of course is indeterminate. This of course is indeterminate. So, we take it as a limiting case. And this will be what? Oh, W, sorry, W. How to find the limit then? It is known to you. You can use that L'Hopital's formula, and that gives Now, you can find what it is. Then of course, you can substitute zeta minus zeta naught as r e to the power I theta and will come as simply sorry q infinity b by r e to the power minus 2 I theta this is 2 that dot as nothing e to the power minus 2 I theta into So, as we discussed that at the beginning that for a Zhukovsky airfoil which is a cast trailing edge, the velocity at the trailing edge is not 0, but is a finite. You can see this is the finite value. Now, we will consider some specific cases. Right now, we have considered an arbitrary location for the center and the trailing edge. Now, we will consider certain specific cases. As an example, if the center of the circle coincides with the origin, or if it is shifted somewhere along the real axis or along the imaginary axis or at certain angle to the both, what type of airfoil or what type of shape we are likely to get. We will consider those specific examples. The first case we will consider is where the origin coincides with the center, that is that zeta naught is 0 and the parameter b equals r. what will happen then? If the parameter b equals r, the radius of the circle, then both the critical point are on the surface of the circle. When b equal to r and the origin is placed at the center, then both plus b and minus b, they are on the surface of the circle, the front point and the rear point. And obviously, the geometry in the real plane or the in the z plane will have two sharp corner corresponding to z equal to b and corresponding to z equal to minus b, both. Okay. Now, of course, we will see what that geometry looks like otherwise. Oh. Anyway, we will not be able to finish it today. So, we will stop here and continue with this the next class.